Problem 1 from the 2009 test. They start by giving us this electric potential, which is a little intimidating at first, but it's not going to be as bad as we think. This is the electric potential when we are inside the sphere, so for R less than big R. This is the electric potential for R outside of the sphere. First thing we want to do is we want to indicate the direction of the electric field and then derive an expression. So since we're deriving an expression, we need to start with an equation from the equation sheet. In this case, we will be taking minus the derivative of the electric potential to find the electric field. I don't think this is intuitively obvious, but since there's a minus sign out inside here, and because R is going to be less than big R right there, you can see that we're always going to have a negative for the electric field. So the electric field in the inner part of the sphere is going to be pointing inwards. I don't think that that's very intuitive. Don't stress too much about that. The best thing you can do is just take minus the derivative with respect to R. Very simple derivative here because we only have one term with R right inside there. So this term goes away. That's why this term is going to always be positive. Minus sign out front means that the electric field is going to be inward. We get this for the electric field after taking the derivative with respect to R. Taking the derivative with respect to R for the outer electric potential is far easier, and we get the electric field as expected, Q over 4 pi epsilon naught R squared. That's going to be radiating outward. We pick up a minus sign from the derivative on 1 over R. That cancels out the minus sign in front, so that electric field is going to be radiating outward. Dramatic pause. Okay. Next part, for the following regions, derive an expression for the enclosed charge that generates the electric field in that region. We're going to be relying on Gauss's law, so I wrote down Gauss's law for the derived part. The closed surface integral E dot dA is equal to Q enclosed over epsilon naught. In this case, we will be using for that inner region 4 pi R squared is equal to Q enclosed over epsilon naught. We're trying to find Q enclosed, okay? We replace the electric field that we found in the previous part, so that's the electric field from part A for the inner region. We divide the 4 pi R squared over to the other side. We solve for the Q enclosed by bringing everything back over, and we get this guy for our Q enclosed. Allergies. Very easy to find Q enclosed for the other region. We know the electric field from before. We're trying to find Q enclosed. We're still doing a 4 pi R squared over there. So we get a Q enclosed is equal to Q naught. That one is pretty straightforward. I think I might have a slight error. No, it looks good. Okay. The next part, you're going to use Gauss's law to figure out the charge on the surface. Since we know that this is the overall Q enclosed when our Gaussian surface is outside of the region, that must mean that that's a combination of whatever charge is on the surface and the charge on the inside. Since this Q naught that we found here was not equal to this Q right here, since they're not equal to each other, there has to be charge on the surface. So the charge on the surface is going to be the difference between those two guys. Notice that for the inside, I'm going to replace that R up there, that R cubed over big R cubed. I'm going to replace that with R is equal to capital R because we are at the surface of the sphere. So this whole thing is going to condense down nicely to minus 6 Q naught. We have a Q naught over here. The charge on the surface has to make it so that charge on the surface minus 6 Q naught is equal to Q naught. That means that the charge on the surface is 7 Q naught. So keep in mind this technique for using the Gaussian surface to figure out the charge on the surface. Usually we don't have to worry about that kind of thing, but since this was a non-conducting sphere, so it was a spherically symmetric charge distribution, we couldn't rely on any tricks. So the trick we're actually going to rely on is outside we know what the Q enclosed has to be. That has to be a combination of the other two charges. Finally, they just want the force on, let me make sure I get the terminology right here. On the axis below, sketch a graph of the force that would act on a positive test charge in the region R less than R and R greater than R. So in this region, we have a negative force that is getting bigger and bigger and bigger as this R increases on the Q enclosed. Look at the previous slide if you need to see that. And then it dies off as a 1 over R squared potential as we move away. So pretty straightforward problem, a little intimidating on that electric potential at the start, however.